this the homework you. I'll be traveling between November 16th and December 2nd. So that would be before Thanksgiving. I'll give you 1 week break. So before Thanksgiving, I'd like to give you a take-home exam. And you have more than 2 weeks to work on it. And then I will also give you a list of term projects so that you can start working on a term project before Thanksgiving. And term project will be due the last day of the exam will be, I guess should be maybe 18 or 19. I don't remember. Maybe 19 or December. Okay, so you have plenty of time to do your take-home and also your term project. Is that fair? Okay. Any questions before we get started? Okay, I'd just like to wrap up on the fast multiple algorithm method. The method actually was first developed for statics or for Coulombic potential. In astronomy. You know, the astronomy, the Earth's gravitational field is the Coulombic potential because the force is proportional to 1 over r squared. Okay, the potential is 1 over r, but the force is proportional to 1 over r squared. So it's like Poisson's solution or Laplace solution. And at the time, there was a guy by the name of Apple. He actually developed a fast method of doing this thing by factorization of the Green's function. Essentially, the Green's function is factorized even for Coulombic potential in this fashion. Okay, we show how to factorize this for dynamic field, but it turns out that for Coulombic potential, this is also possible. And then there's for 2 astrophysicists from Princeton, I believe, Barnes and Hutton. Okay, they further worked on this, also doing similar things like this using factorization. And then, by the time comes, and then it was Greengard and Rocklin. Greengard was the student of Rocklin. They make this fast multiple algorithm a lot more systematic, also using this factorization concept. And that must be late 70s and so on, or early 80s perhaps. And then this might be maybe late 70s and early 80s. Then these things work very fine and dainty for static problems, because static problems are actually quite simple to work on. The physics is rather simple. The static problem has the property that the field cannot carry information. The 1 over r field cannot carry information. In the sense that if you have a 1 over r potential, if you differentiate it once, you get 1 over r squared. If you differentiate 2 times, you get 1 over r cubed. If you differentiate it 3 times, you get 1 over r fourth. What it means is that if you have a 1 over r potential, what this means is that the further you are from the source, the smoother the field. Okay, this is what it means. Higher order derivatives becomes increasingly smaller and smaller and smaller the further you are from the source point. Another way of saying this is that this potential cannot carry information. It cannot be used for wireless communication. You cannot use your cell phone as static and expect it to transmit information across the universe. Okay? But the dynamic potential has quite a different property. If you differentiate it once, okay, you get 2 terms. You get 1 over r squared term. You always get this term. And this always the case is 1 over r squared plus higher order term. Okay, if you differentiate 2 times, you will still get something like this, but high order term. And so on and so forth. If you differentiate it 3 times, you always get a term that decays as 1 over r. So there's always a term that decays as 1 over r irrespective of how many times you differentiate the potential. This is the wave dynamic potential. What it means is that this potential looks something like this. And no matter how many times you differentiate it, there's always a term that drops off as 1 over r, which means that you can encode information in this field and let that information traverse as 1 over r. That's what it means. This is what this mathematics means. So it's a lot harder to develop a fast algorithm for dynamic field compared to the static. This is dynamic. This is static. This is what Earth gravitational fields would look like. That is what the electromagnetic wave field would look like. And we can use electromagnetic wave field for wireless communication. So because of this, you can easily show that this factorization that you have in static, because of this property of the fact that information travels only a short distance away. If these 2 points are far apart, you can easily show that if I start with P by M, M by M, M by P, I can show that for static, M is much, much larger than P because of this physics. Okay, you can factorize the Green's function in such a way that the centerpiece only needs a few terms. Whereas you might start with many, many multiples, but the moment you go far away from the multiple sources, you only need a few multiple terms to approximate this field. This factorization is very easy to do. And because of that, you can gain in efficiency very easily that by just putting the source in a few points far apart. Okay. However, if you were to perform this factorization, IL, L prime, beta, L prime J. If this is, actually this should be enough. This is column vector, so I shouldn't call it P by M. I should stack this into a matrix system. Okay, I can stack this into a matrix system, and if the system is P by M, and if I make this into a matrix, okay, the factorization of the matrix will be such that if this is P by M, this is M by M, this is M by P, then you'll find that this M can be much smaller than P because this system does not carry information long distance. Similarly, I can stack this into a matrix system, okay, and I will have a factorization something like this. This might be P by P, this is P by P, this will be P by P kind of thing, okay? And then it is not possible to make this term small because of wave physics. Information is always traveling long distance. There's no way to reduce the information so that it can only be carried by a few multiples. You always need at least a finite number of multiples to carry this information long distance. Hence, this cannot be reduced to a small matrix like in the static case. So what we need to do then is to diagonalize. The next thing we do in order to improve the efficiency of this algorithm, we have to diagonalize this center matrix. And essentially, that was what we've been talking about in the last lecture. And the first proposal for diagonalization was given by Rocklin. Okay, he suggests that in order for this to work for wave physics, you actually have to diagonalize the central matrix. But however, he and his team couldn't get this algorithm to work well. They spent millions of dollars on this algorithm. and they couldn't get it to work well. And the reason why they couldn't get it to work well is because they missed the very simple physics of wave physics. Okay, let me tell you what that simple physics is. So let me just talk about the aggregation part of the algorithm, which is to find the radiation pattern. Okay, the aggregation part of the algorithm is that if we have a whole bunch of sources, okay, and the first part of the algorithm is to find the radiation pattern of these sources. So I can simply write it as AI e to the I k j dot Ri. Okay, Ri being the location of one of these sources. Okay, Kj being the observation point. And this might be at a position Rj. So when you look at this vector is Kj. Okay, and this is essentially finding the radiation pattern due to all these sources. 1 to m. If I have m sources over here, I have to find a function of alpha. This will give me something like Kj, actually K cosine of alpha j times Ri. Okay, this after performing the dot product, I will get that. And you see that the larger Ri is, the more rapidly varying this function would be. Can you see that? If Ri is a large number, so if I change my alpha, which is changing this angle over here, okay, this angle might be something like this over here, and it will vary rapidly as a function of angle. Okay, the larger Ri is. So if this group of sources occupy a very large space, such that this number is large, this will be a rapidly varying function of alpha, which means that you need to have a high sampling rate to capture this radiation pattern. In 2 dimensions, alpha will be a function between 0 and 2 pi. Okay. In order to capture the radiation pattern of this, you will need to sample the radiation pattern at a very high sampling rate. And then the sampling rate is roughly proportional to KRI. Okay, that is the sampling rate. The number of sample points you need is roughly proportional to Ri max. I take the maximum one that is on the peripheral. That will give me the most rapid variation. And the most rapidly varying part of the contribution to this summation will come from the peripheral of this group over here. And my sampling rate has to be at least proportional to that number. Okay? And so roughly, if this is L max, if this thing is of L, roughly P is proportional to KL. Roughly. Okay, P is proportional to KL. Which means that the larger the group size, the more sampling points that I need. And so if you perform this calculation naively using a straightforward calculation, then the cost is proportional to P times n, because you have to do this n times. And for each calculation, you have to produce P points on the left-hand side. It's very costly. This is roughly n squared. A very, very costly kind of calculation, which is the naive calculation, is proportional to m squared. It's not at all efficient. How can I make the calculation of the radiation pattern more and more efficient? I can use a multi-level approach. First, I divide these sources into group of sources by partitioning my region into smaller and smaller boxes. Okay. So I can have many sources distributed within these boxes. What I do first is to take the smallest box, and if I'm lucky, I might only have a few sources inside, and then find the radiation pattern due to the group of sources within this box. Okay. Then the bandwidth, okay, P0 at the lowest level is proportional to K R0 max. That is, the largest size of this box is roughly R0 max. So my sampling rate can be very slow, very small. So in order to capture the radiation pattern of this small group of sources, I need only to sample at a few points to capture its radiation pattern. I do likewise for all of these things. Okay. So my workload is number of radiation pattern times the number of sources. Okay, number of sources would be maybe say M. So my workload at least would be M0, P0. M0 being the number of sources I have within each of this box. Okay. Then the next thing I need to do then, having found the radiation pattern of each of these boxes, I need to find the radiation pattern of all the sources within this box. Okay. So I know that in order to capture the radiation pattern of all the sources within this box, then the P1 should be proportional to KR1 max. Okay. These radiation pattern of these sources will be more rapidly varying. Hence, I need a higher sampling rate. Okay, R1 max. And R1 max is roughly equal twice R0 max. You agree? Because these boxes are twice as big. So I need about twice the sampling rate. So I can repeat the same thing after having found the radiation pattern of these sources. I can shift the coordinate system using the translator. In this case, it's a very simple translator. It's just this kind of shift. Okay, just this kind of shift. In 2D, just a very simple shift. The translator is very simple. And then I can shift it to the larger box and then create the radiation pattern of this larger box. I can do likewise all these boxes. And then after having found the radiation pattern of this larger box, I can group them again to find the radiation patterns of these larger and larger boxes. Okay? In this manner, I can find the radiation pattern of all the sources in N-log-N operations. Okay? But it's not possible unless you do one thing, which is interpolation between levels. Okay, interpolation between levels. In other words, you take the sampling rate of the smaller box, you interpolate it to a higher rate before you translate to the radiation pattern of the larger box. And then having found the radiation pattern of this larger box, you interpolate to a higher sampling rate before you use it to find the radiation pattern of the larger boxes. Okay? And then you do likewise. And it's only with this interpolation, the very simple thing, that you can reduce the complexity to N-log-N. Apparently, the group of mathematicians didn't know about this guy. So they kept using this naive method and then doing multi-level, and they could not get N-log-N complexity out of this kind of very simple thing. If you understand the physics well, you would see that immediately you need to sample the low and smaller boxes at a low sampling rate. You need to sample the larger boxes at a higher sampling rate. And they're not compatible because all these sampling rates are done in a circle, and hence you need to interpolate between these levels. Okay? Yes, someone has a question.
What do you mean by interpolate? How are you doing this?
What is this?
What do you mean by interpolate?
Interpolate means that, say, if I have found the radiation pattern of this, I look at the Nyquist theorem. They have a very low frequency content. So if I look at this function, they're all periodic. I mean, they're all periodic functions, 0 to 2 times. And at the low level, the function might be f of alpha. It's a periodic function of alpha. Okay? I look at this and say, Nyquist theorem says that I only need 2 points to capture this function precisely. Or maybe Nyquist theorem says I need 4 points to capture this function to within exponential error. Okay, because this is a n-limited function. So maybe I store this with 4 points, and then going to the next level, I know that my boxes will be twice as large. Okay. Then the radiation pattern of the box next level up might not be so benign looking, might look something like this. So periodic. Okay. Then I know that maybe I need to sample this at 8 points in order to capture. Maybe it might not be that nice, it might be something like this. It's periodic, but I need to sample at 8 points. In order to move the data from this box to that box, I interpolate this to 8 points. And then before I collect the radiation pattern from them and create a radiation pattern for the larger box. I do likewise. Okay, I do likewise. And then what it turns out then is that at the bottom of the tree, if I write this algorithm as an inverted tree, it will look something like this. Each node has 4 children. 4 children. Okay, you know what I mean. I've not drawn a very good tree. Okay, each node has 4 children. So what happens is that at the bottom of the tree, I have many boxes to work on. Okay, the number of boxes that I have to work on is roughly proportional to order n. Okay, because say I have only 2 or 3 source points per box. I have order n boxes to work on. And then the next level up, the number of boxes is 4 times more, n divided by 4, right? Because the boxes are larger. Okay, but then the sampling rate goes up higher. Okay, the sampling rate goes up twice as high as I increase to the next level, I think. And then over here will be n over 4 squared. Over here will be n over 4 cube or something like that. The number of boxes I have decreases in an exponentially fast manner as I go up the level. But the workload also increases twice as much as I go up. Okay, here I might have 2 times more, I will have 2 squared more work, I have 2 cubed more work. Okay. Finally, it turns out that the workload is order n per level. It turns out to be order n per level because the sampling rate goes up, the number of boxes declines. So it keeps the workload order n per level. And finally, because I have log n level, if you look at the number of levels over here, log n levels, then the workload needed to find the radiation pattern of such a source is order n log n. And this was overlooked by the other researchers, and they couldn't get the algorithm to work. So Jiming Song and Chai Chen Lu and I worked on this algorithm, and we were able to, for the first time, produce an algorithm that can solve a dense matrix system on a workstation with 100,000 unknowns. Okay, 100,000 unknowns. Okay, and when I told this to Rockland, he was exhilarated. He was so happy. He said, wow, see, my algorithm works. He said, my algorithm works. Okay, so but he actually worked with his team for a long time with on the West Coast as well, and they couldn't get it to work. He was exhilarated that we can get a dense matrix system of this order with about 100 megabytes of memory, actually, 120 megabytes of memory. Okay, 120 megabytes of memory, and that was actually quite phenomenal because at that time, nobody could solve a dense matrix system above about 10,000. Okay, if you want to solve a matrix system that was dense, above 10,000, and you will have to use the largest supercomputer. You have to go to NCSA to plead for some computer time to solve a matrix system of about 10,000 unknowns. But then we show him that with the workstation we could solve such a large problem. But I'm only telling you half the algorithm, the aggregation part. With this aggregation part, you can read up yourself. It's a lot more complicated. Okay? It's a lot more complicated. But this is essentially the physics behind why this algorithm works, why you need interpolation, and in the opposite case, in the disaggregation case, you have to do something called interpolation. Okay, interpolation in the opposite sense. As you aggregate the information and distribute them down the tree, you have to do disaggregation. And this is essentially the physical reason as to why dynamic algorithms are a lot more complicated. They need a lot of work to work on. Okay? And I think so far, we call this a multi-level fast multiple algorithm. It's the only working algorithm that can produce n log n complexity for wave physics problems. A lot of people claim that wavelets can do that. A lot of people believe that QR decomposition, low rank approximations can do that. But they don't have a proof. And usually I don't think those algorithms work for wave physics. We need actually to diagonalize the system in order to get this to work for wave physics problems. So are there any questions regarding this? Yes?
So when you aggregate, does it matter about the order of interpolation and translation? I mean, you first interpolate and then translate, or you first translate and then interpolate?
Well, I would actually first interpolate and then translate. Okay, because if you translate and interpolate, then you're actually doing things in the wrong order. Because what happens is this, that when you go from one level up, okay, maybe you have alpha, you have to multiply by this function. And then you produce the radiation pattern at the next level up. Okay. You have to multiply this pattern. This is the translator in the Fourier space. Okay. So if you translate and then interpolate, you miss this part because this actually contributes to the high frequency component of that. So it's better to raise this to a higher sampling rate, interpolate, and then give this radiation pattern. If you multiply this by this, you already increase the sampling rate. Your sampling rate that you have, which is a low sampling rate, might not be able to capture this term after it has been multiplied. So I will interpolate first before I translate. Okay. Are there any other questions? Right now, some people in the world, I just got an email from a guy from Belgium. He said he has used this algorithm to solve up to 4 billion unknowns, dense matrix system. Okay, a guy in Spain solved up to 1 billion unknowns. My former student, Levan Korea, solved up to 500 million unknowns. And then there was one guy from Beijing who claimed that he can solve 1 billion unknowns too. So with this kind of algorithm, previously you could only, without this algorithm, you can only solve 10,000 unknowns, but people can go up to a few billion unknowns now with this kind of algorithm. Okay. Are there any questions? If not, then I move on to a new topic then.
Do they give professors raises when something like this happens?
Well, somehow they do, I think. Yeah, they do give you some brownie points.
Oh,
Yeah, they do.
but it's not brownies.
What?
Never mind.
So, Part 2, can you talk about the fast homogeneous with bandwidth algorithm?
I'll talk to you on private on that. I think I cannot talk to you in this lecture. Okay, I can talk to you personally on that algorithm. So I think the next thing I'd like to talk about is actual photonic crystal. I think a lot of you know about this. It's not in my textbook, but I'll give you extra notes to read about this. This work actually was inspired by what has been done in electronic crystals. In electronic crystals, we have atoms that are organized in a very periodic fashion in a crystal lattice. And when you send electron wave, okay, when you send electron wave through this crystal, the electron wave function will be diffracted by this crystal lattice, and then you can have what is known as the band structures. So if you look in electromagnetics, we always talk about omega k diagram. Okay, but then in physics, we always talk about energy k diagram. Okay, energy is h bar omega, so it's actually the same thing. You may get band structures that look like this. Okay, so these are band structures. And then there are certain frequencies where no k exists. These are called band gaps. Band gaps. Okay, and then the other one is called the band pass region. And similar kind of ideas have also been used in microwave filters for a long time. For instance, if you have a waveguide, if you start adding corrugation to the waveguide, you can show that because of the constructive and destructive interference that happens in this waveguide, you might have band structures that look something like this, that above a certain frequencies, that the wave cannot go through, and then you might have something that looks like this. Okay, corrugated waveguide, for instance. Okay, and then somebody had the idea of why don't we try to imitate what happened in the electronic world with photonic crystals. In the electronic world, the wavelengths of electrons are very small, maybe on the order of nanometer size, okay? But then in the optical world, wavelengths are on the order of hundreds to 1,000 nanometers. So wavelength is a lot larger for a photon in optical frequency compared to wavelength for an electron in the crystal lattice. So it's possible to make artificial crystals and then study the effect of artificial crystals on the propagation of photons in the crystal lattice. So I think the first guy who proposed this was called Low Mo. Maybe no. I'm not sure. Okay, he proposes that we do this kind of thing, and it has become quite an interesting topic of study. But much of this actually is inspired by what happened in solid-state physics and the electronic world. So this is the world of solid-state physics. Okay, so let's look at photonic crystals. I think a lot of you know about this, and especially if you took my quantum mechanics course last semester. I talked about it last semester. So this will be a repeat for some of you, but maybe something new for some of you. Okay, so let's see what we have, what kind of concepts we have here. So if you have a lattice, you assume that you have an arrangement of scatterers that are periodic in a certain fashion, that you have a lattice vector, that the lattice vector has this property that it is N1A1 plus N2A2 plus N3A3. These are unit vectors. A1, A2 not unit vectors, sorry. A3 are lattice vectors. Okay, it could be this vector. In 2 dimensions, it could be this vector and that vector. So if you have linear superposition of this vector, and in 3 dimensions you have to add a third one, n1, n2, and n3 are integers. If you have any linear superposition of these vectors, if you translate the coordinate system by that much, the problem remains invariant. You translate the problem by this amount, you should get the original problem back because of the symmetry of it. Okay? So this usually happens if the potential of the scatterers have this property that they have this translational invariance. So we can propose what is called a block locate wave, or the block locate theorem. Okay, let's first think about what happens if there's no crystal lattice. If there's no crystal lattice, we can always have a wave solution of this kind, e to the I k dot r, that goes through the system with no problem. Okay, this wave will travel through the homogeneous space. This is homogeneous space. And what happens if you start to put in scatterers in this homogeneous space? In addition to this wave, which can be thought of as an incident wave, you have scattered wave. So in total,